Okay, good morning, everyone. I hope everybody had a good afternoon yesterday. You're doing lots of math in your free time, right? Yeah, good, good. Okay, so we're coming down to the end here, and this morning, Elena will give the last of the three talks about Hilbert functions of points. Okay, go ahead, take it away, Elena.
Thank you, Adam. Okay, just want to say something about my talk yesterday, because I stopped with 2 points, and then I'm just wondering to ask you if you are able to compute the Hilbert function of three double points. There's a problem. So they have to study also. I'm just kidding. That's okay. Because I hadn't the time to finish, of course, just to complete, because 1 point, 2 points, they are easy. But okay, I'll help you. But when we have 3 points, how can you draw 3 points on a plane? We are on the plane, so we are easy case, okay? How can you draw 3 points on a plane? How many choices do you have? 2, of course. So this means, so we have 3 general points. That means that they are not on a line, or they can stay on a line. So we have different Hilbert function, even from the support, because in this case, in the first case, there is no any line contain these 3 points. In this case, even the support, of course, there is a line contain these points. So since I don't want to take much time from the talk in P1 cross P1, I give you the answer. And then, so these are 3 general points. And from my talk yesterday, then you can use Alexander-Ishevitz theorem, okay? So this is not one of the exceptional cases. So each point has degree 3. So these 3 double points has the behavior as 9 distant points. It's a scheme of degree 9. So the Hilbert function, 1, 2, 3, is just the maximum that you can get. And then it's a 1, 2, 3. 6 and 10, 9, because it has degree 9, okay? So this one, so these are general points. And this is, you can do this by hand as we did yesterday, but in 1 minute, I hope to give you one of the way that you can get the double points. And you can get this from Jeremita Migliore Saburin. I will give you the reference in my note. I'm just fixing my note and put everything share with you. So we have 6 points here. So we have 1, 2, 3, 4, 5, 6. And then when you remove 1 here, then you can get a line with just remove 1 in each point, and then you get 1, 1, 1, and then you shift it by 1 this end, and then you compute and you sum this one. And this is the first difference of the Hilbert function. So the first difference of the Hilbert function, so it's just given by the first is 1, and then it's just the difference between the hi minus hi minus j. So you can recover the Hilbert function from this guy. So if you have 1, 2, 2, 2, 1, 1, so the Hilbert function will be 1, 3, 5, 7, 8, 9. So this is the Hilbert function. And you can get this even by Bezout theorem, okay? I've just shown you this because Adam and I, we just did for any multiple, because this is a special case of a complete intersection of 1 line and 3 lines. A totally reducible complete intersection of type 1, 3. So 1 line and 3 vertical lines. So we have a result for any complete intersection A, B with multiplicity M. So, but I have no time, of course. Just so because, as I told you, when you go on with the number of points, then if you have 4 points, though they have many different configurations. No? So for each configuration, you have, of course, different Hilbert function, both for the support and, of course, for the double. So, for example, and then I stop. There is a paper with me and Brian Arbor in very past, it was 2003, maybe 4 or 5, I don't remember. So we just classify the Hilbert function up to 6 points in the plane. So it seems very easy, something really, 6 points, but 6 points up to isomorphism has 11 configurations, 11 configurations of points. And just to let you know that Brian with Geramita and Migliore wanted to do the 7 case or 8 case. And if I don't remember bad, they came up with 147 or something like that. So at least 100 sure. I remember it was 47, 40. So as you can see, it's not easy. It's easy to state the problem. It's not easy even if you specialize the support. Of course, we wanted to study any kind of configuration of points. Okay, so see, this is just to complete the argument, because I stopped with 2 points that were easy, and then you see is it always easy? I gave you a hint how to compute the Hilbert function, which is just a computation. It's mostly Bezout theorem, so everything seems easy, but it's not easy at all. Okay, for general collection points, still open problems up to multiplicity m. Then we have a result, but of course we can refer to Ciliberto and Miranda papers. I will give you my notes. I will share my notes with all the reference that, not all, I mean, almost all, of course. Okay, let's go back to P1 cross P1. Before starting, of course, my point of view, you have heard about P1 cross P1 from Christine. But if you remember, I told you one last day, just focus on some blackboard where there was 2 special points, and then you know the idea of these 2 points. So almost I have an hint how to compute this ideal of points. So my point of view is different, because it's true that we are working in P3, in the projective spaces 3. But I've learned from the first year of the graduation, at least in Italy, that we learned that a smooth, a reducible quadric, it's a ruled surface. Do you know this? So think on a hyperboloid hyperbolic. If you see it drawn like this, and then if you saw a picture, then they are drawn with some lines in this way, some other lines in the other way. I don't know if you study it, but the reason is because you can take the equation of a smooth reducible quadric in P3, and then you can write down the equation to rulings of lines. With the property, the lines of these 2 different rulings are skew, and lines, so if you just see a picture, and lines of the other rulings intersect on a point. So this is why also the reason why they are calling ruled surface, because the equation of smooth reducible quadric can be written as 2 ruled system. I say in Italian system of lines, so there are rulings with the property that lines of the same ruling are skew, and the lines of different rulings intersect on a point. So my point of view on looking at P1 cross P1 is this one. So I'm going to talk about points as subscheme of the quadric, not as subscheme of points in P3, because it's different, because the quadric has dimension 2, so the length of the resolution can be 2 or 3, since the depth of the ideal can be 1 or 2. So it's a different perspective. It's true that the idea, the polynomial ring, formally, it's in 4 variables like P3, but then we put the bigrading. So we look at the polynomial ring with bigraded, but then the scheme is a subscheme of the quadric. Also, there is an exercise from Archon book that asks you to show that any smooth irreducible quadratic is isomorphic to P1 cross P1. So this was my starting point, even for my PhD thesis, not for reduced points, but for fat points. Reduced points were studied by Giuffrida, Maggioni, Ragusa. Ragusa was my supervisor, and Giuffrida and Maggioni were professor geometry in Catania. So they studied these points, and then I realized that I could study even fat points. So today I'm trying to give you an idea, because of course I would like to be as simple as I can to show some of the properties. Okay. So let's start with, I'll try to, so the main reference is my book with Adam. This is Adam, I think. Arithmetically, Cohen-Macaulay. In P1 cross P1, and it's published in Springer in 2015. Okay. Also, there is a fact that while points in Pn are always Cohen-Macaulay, this is not longer true in P1 cross P1. As I said before, the length of the resolution can be 1 or 2. So we can have points that can be arithmetically Cohen-Macaulay and points that are not arithmetically Cohen-Macaulay. So we have a lot of equivalent properties about arithmetically Cohen-Macaulay, but in P1 cross P1, even, so think nothing with other multi-projective spaces, there is no any Macaulay's theorem. It's still for P1 cross P1, it's still open. What does it mean? In Adam says that if we have a no sequence in Pn, let's say in P2, then there exists a set of points, a reduced set of points with that Hilbert function. This is no longer true in P1 cross P1. Even if we have a nice bigraded Hilbert function with every good nice properties, that is not longer true that there exists a set of points with that Hilbert function. So it's still open problem. So still when you want to classify a small number of points, then you can get troubles. Okay, so it's still open problem. So if we focus with the arithmetically Cohen-Macaulay schemes, I'm going to give you the definition in a few minutes, then we can say a lot. So my goal of this talk, if I'll be able in time, is to give you how we can recover these arithmetically Cohen-Macaulay properties even from a combinatorial point of view, because they share a nice combinatorial properties. Okay, so K is still our field of characteristic 0. And as I said before, R is our polynomial ring in 4 variables. So formally, they are, it looks like P3, but then we give different grading. We say these are by degree 1, 0, and the degree of y0, I think also Christine said the same thing, okay? And I look at P1, okay, let's say, okay, P1 has P1 as this, so we have tuples, A0, A1, B0, B1. So I constructed my P1 cross P1. And this is in k squared times k squared. And then where we have that they are not zero, okay? No, they are not both zero, okay? So this means that neither A0, A1 is 0, right? It's right in English. Under the equivalence, there we say that this A0, A1, B0, B1 is equivalent to C0, C1, D0, D1 if there exists lambda and nu in K such that they are, this is multiple and this is multiple. So A0, A1 can be lambda C0, C1, and B0, B1 is nu D0, D1. And we define our class, our equivalence class, we denote the equivalence class as in this way. Just recall this symbol that will be the coordinates of my points. So the coordinates of my points. So, and also since we have the by grading, then in n, I put 0, okay? So start with 0, okay? This is my n. Then I need to consider an order. So my order is that a pair AB is, let's say, less than in this way, CD. Okay, as usual, is if and only if A is less or equal than C and B is less or equal than D. So for you, are comparable this one? No, okay, so they are not comparable, okay, because this is bigger than this, but this is not bigger than this, okay. If M is a monomial in R, so it's of this type. So since we have the back graduation, so don't look at it as a monomial in P3, so it's a monomial in P1 cross P1. So this has by degree A plus B, C plus D. For example, if I take x0, x1, just take this monomial, which is this by degree? Which is this by degree? 2, 0. Because the sum is 2, and then, okay, of course, we don't say. And this is, so in general, this has by degree in this one. So in R, we also need to get, in our ring, R, we have, we can look at it as a bigraded vector space. So this is, if this can be like written as the sum of Rij, the vector spaces on K spanned by all the monomials in degree Ij, with the property that is such that, so Rij is a K vector space spanned by the monomials in by degree I J with the property such that, okay, with the property that Rij are composed RKL, this is inside Ri plus K, J plus L, and this is for all Ij and KL in N squared. So let's now define the ideal. So, of course, an ideal is defined by bihomogeneous form. So a bihomogeneous form is a sum of monomials, binomial monomials in by degree. So we have that if F in our ring is let's say that F is bihomogeneous. Of course, if F can be written as by degree monomials in, okay, bihomogeneous in degree, let's say Ij I'm used to skip the by, okay, because for me it's migrating. So sorry for me, even if I say degree, everything is by degree, okay? In degree, Ij. So what are our by homogeneous ideals? So, of course, every ideal that is generated by binomial polynomials. Sorry, are in English it's written bihomogeneous polynomial. Bihomogeneous polynomial, okay? And so this ideal also inherited the bigraded structure, so can be written as the sum of vector spaces in by degree Ij. So our quotient ring will be just a module of Rj over Iij, okay? So set Ij, of course, we are intersecting our vector spaces, intersect I, okay? So we can get all the binomial, and Ij is a subvector space of Rij. And so we have that in particular, I is just the sum of all the pieces, if you want to put the comma or not. So this means also that our quotient ring can be written like as the sum of Rij over Iij. Okay, so this is for Ij in N squared. Okay, so this is more or less a repetition of what we know for usual graduation, but this is how we translated it by graduation. Okay, so a point P okay, I'm just defining my object. So this is the ideal. So, and if I have a point, in P1 cross P1, then is we denote its ideal as usual by P, of course, or it depends on the context also, IP, okay, it depends on, and it's defined by all the bihomogeneous form in R, of course, such that F in P is equal to 0. So the definition formally is the same as in Pn, okay? There is no difference. The difference is only that we are looking at P1 cross P1. So now we are interested in what? We want to find the Hilbert function of a set of points that vanishes in certain the Hilbert function of points in P1 cross P1, not only reduce it, in generally the question is with any multiplicity. So we translated the interpolation problem in Pn in P1 cross P1. So now we define the Hilbert function in by degree ij, and then I'll try to compute to make some examples. So define the, okay, it's bigraded Hilbert function, and at the beginning, Giuffrida, Maggioni, Ragusa call it Hilbert matrix because since it's bigraded, it has the shape of an infinite matrix. Okay, but then we change. Of course, it's a Hilbert function. It's a Hilbert. So if you go back in the literature, you can find Hilbert matrix. So it's the same, but we change it as Hilbert function, and of course, our Hilbert function, as I told you yesterday, I've always used to consider the module. So it goes from n squared to n. So, and it's defined by, so maybe you can see here. So h in degree ij, as usual, is the dimension as vector space of Rij of the monomials in degree ij minus the dimension as vector space of our ideal in by degree ij. And the number of monomials in by degree ij is I plus 1 times j plus 1 minus, so this is the Hilbert function, and it looks like an, so, and here you put, let's say this is R and this is I, and this is what J. So these are the by degree, blah, 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 and in by degree 0, 0 by definition is 1. Okay, so we always 1, and then of course if we can have 2, I mean 2, it depends on what we are doing. Let's make an example. For example, if we have if the ideal is so if the ideal is 0, which is the Hilbert function, so if it's 0, which is the Hilbert function? See? Yes, it's just J because it's just on the dimension K R I J minus the dimension of I is J. This has nothing, so it's just I plus 1 times J plus 1. Okay? And if I have a point, example 2, in case I is generated by these two linear forms, so x0 minus x1 and y0 minus y1. So it's generated by two linear forms, one in degree 1, 0 and one in degree 0, 1. So it has one generators in by degree 1, 0 and 0, 1. So which is the Hilbert function? It's 1 point. So here we have 1. How many monomials in degree 0, 1? 2, because it's plus 1. 2 minus 1 is 1. And then once it's reached the degree of the scheme, it's 1 forever, okay? How many curves in degree 1, 0 monomials? I say always curves, okay? In degree 1, 0, we have 2 minus 1, it's 1, okay? So we have, so the degree, we have 1, the degree of x0 minus 1 is, do you agree that is 1, 0? It's, and do you agree that the degree of y is 0, 1? So that all the monomials in degree 1, 0 are 2 from this formula, minus 1 is 1. All the monomials in degree 0, 1 are 2 minus this one, so is this one. And then since 1 is just the degree, because it's just 1 point, then it goes 1 forever. Okay? Now, this is 1 point. Let's, okay. Let's take this example. I'm not saying nothing about the point, but take this example and tell me if it reminds you something. So we have x0, the intersection of, and then I'll give you, right now you think this is x0. I think Christina showed you that this one, right? Okay. And then on a few minutes, I'll give you how to draw points, okay? So I think you already have seen this. If you go back to Christine's notes, and if you remember, I told you just focus on that one. So it's an ideal in P1 cross P1 that has 1 generators in degree, which is the degree of x0, x1, 2, 0. 2 generators in degree, 1, 1, and 1 generators in degree. Okay, so I just write okay, let's compute the Hilbert function. So do we have any generators in the ideal of degree 0, 1? No. So which is the answer here? 2. 0 as a generators, but the Hilbert function as module, okay? So it's the number of monomials in degree 0, 1 that is 2 minus 0, so it's still 2, okay? Do we have generators in degree 0, 2? Yes, we have 1 minimal generators in degree, they are minimal, right? So minimal generators in degree 0, 2. So the number of the monomials in 0, 2 is 3 minus 1, so it's 2, okay? And then since it's 2, that is the degree of scheme, I'll tell you soon that these are 2 points, then it goes in this way. But we can also make, we haven't minimal generators in degree 0, 3. So we have to be careful in writing the generators, so taking from the multiple of 0, 2, okay? Then go to 1, 0. Do we have generators in degree 1, 0? No. How many monomials? 2 minus 0 is 2. Do we have a monomial in degree 1, 1? Yes, we have 2 minimal generators in degree 1, 1. How many monomials we have by degree 1, 1? It's 2 times 2 is 4. I plus 1 times j plus 1. So 2 times 2 is 4, minus 2 is 2. Okay, still 2, 0. 2, 0, the same. So in 2, 0, we have just 1 in 2, 0, and then it's 2 as before, because it's 3 minus 1 is 2, and then it goes in this way. It goes forever by 2. So, but this, what I need also, so this is the Hilbert function. Before I was telling you about the first difference of the Hilbert function. So the first difference of the Hilbert function is defined by delta H, that this goes from n squared to n, and it's given by exactly by degree ij, is the Hilbert function. It's the difference between the row and the columns. While in P2 you just made the difference by, it's just one sequence. Here you make the difference between row and column. So ij minus h I minus 1j plus h I minus 1 j minus 1 minus h I j minus 1. And we defined, of course, and okay. No, I have no enough time to go. So if we take the example, so the first example where my ideal was x0 minus x1, y0 minus y1, and we want to compute the first difference of the Hilbert function, then we get, so here I want to say that also delta h in degree 0, 0 is 1, okay? So if we compute the first difference of the Hilbert function of this guy, here we have 1, and then since the difference is always 0, if you make it's the difference, if you compute the difference, then you get that it's always 0. But if you compute the Hilbert function of this guy, the first difference of the Hilbert function of this guy, then you get, so you get 1, 1, 0, 1, minus 1, 0, and then 0, 0, 0. So you can see there are Hilbert function, the first difference that has only 0 and positive number, and Hilbert function that it can have all negative numbers. Well, the difference is that this is correspond to an arithmetical equimacaulay scheme, and that one is a not arithmetical equimacaulay scheme. So roughly speaking, this is the ideal that corresponds in P3 at these two skew lines. In P1 cross P1 is what we say there are two non-collinear points, okay? And this is just the ideal of 1 point. Okay, in my last minutes, I will say, just give the definition. And so the definition is not so different from, this is to make shorter arithmetical equimacaulay set of points. So we say that X, let's say X is arithmetically equimacaulay scheme if R of Ix is Cohen-Macaulay. Just remember that even in this, so there is no any difference about the definition, okay? The depth is equal to the dimension. So this is the depth of R of, sorry. It's equal to the Krull dimension of R of I. Okay, so the definition is the same. But this has a nice combinatorial property in P1 cross P1. So, as I said at the beginning, we have a way to draw points in P1 cross P1. I said that they come from the intersection of two lines of different rulings. So we make, let's say, how we want to draw. And drawing points. So we consider the line we call by HI the lines of the first ruling, and let's say first horizontal ruling. And by Vj, I mean, it's just a way to say first and second, I mean, just a definition. Vertical. This means that this is like H1, H2, so H, but doesn't matter, AR. So this is how we want to draw, and we want to draw our points there. So we define, so this is how so these are the skew lines. The skew lines, and they intersect on a point, okay? So on one point is just intersection of these two lines. So a set of points, I consider the lattice that contains the set of points. So consider X, it's intersect Ij, intersect Vj should be different from the empty set, okay? So if I want to draw one point, if I want to draw this point, and one more thing. So when I want to say, since it's a linear form, they are lines, so they are linear forms in by degree 1, 0. So I suppose that all these R1 are by degree 1, 0, and this is by degree 0, 1. And H1 is like H0, X, A1, X0 minus, remember the equivalence class? At the beginning, I gave A0, A1 times B0, B1. So a point is just the intersection of the line. A1, X0 minus A0, X1, okay? And the vertical line, it should be B1, Y0 minus B0, Y1, okay? So this is, so you can go here. So here it should be like, you start with X0 minus X1, and then you can go minus 2 X0 plus 1, and so on. This is the easiest way to draw this grid, okay? So here, this is what they call H1, and this is what they call V1. So I can draw my point here like this. But if I consider this ideal, so what I'm drawing is just, so let's consider like X0 minus 1. So if you consider this one, this is related to the point 0, 1, 0, 1. So this ideal X0, Y0 intersect Y0, Y1 correspond to the variety given by the point 0, 1 times 0, 1, as I defined before. And this is, it's related to the point 1, 0 times 1, 0. Okay, so this is, if I don't mix it up, so the 2 points are this one. when I said the two non-collinear points. Of course, if you say some two non-collinear points, they just give you look at you as a monster. But that going, of course. But you say what you want to say. When I say in my ambient space two non-collinear points, I'm thinking of two skew lines in P3 that look at in P1 cross P1. Because each of them intersect on a line, but they are not. And as you can see, this is the first easy example of not arithmetically Macaulay scheme. The length on the resolution is as length 3, sorry, the depth is 1. So as a length 2. But I don't have time to talk about the resolution. But I said Ferrer diagram, then how can I easily draw? Okay, I won't have enough time, but just think that this is 1 point, and I have 1 point here, and in the first Hilbert function, I will have 1, okay? So, let X set of points in P1 cross P1. Let us call pi1 the projection with respect to the first coordinate. Onto the first coordinate. And pi2, the projection onto the second coordinates. On the second coordinate, then we should have like something like that. So these are the projection with respect to the first coordinate, and pi2 of x, let's call b1 bd the projection onto the second coordinates. And then we define alpha I, the number of the points with respect to the first coordinates, and the cardinality of the number of the points, count how many numbers as the second coordinates. So alpha I count with respect to the first coordinates, and I will show you with an example. And beta j count the number of points. This is hi, and this is hj intersect x. And call, this is from combinatorics, if alpha of x is just this tuple, then the conjugate of alpha is the following: alpha star of x, that is given by alpha star 1, alpha star alpha 1, alpha 1. Oh, I wrote this, sorry, so don't go. Alpha 1, where alpha star j is just the number of alpha I in alpha x that are bigger, or alpha I that are bigger or equal than j. I'll show you an example. So, if, for example, for the easiest point, we have just 1 point. So this is alpha of x is just 1, nothing. Beta is 1. And if we have the two non-collinear points, then we have that alpha is 1, 1, and also beta of x is 1, 1. But what is the difference? This, if I made a beta of x, it's still 1. So if we make the conjugate of alpha, then it's still 1, because there is not, it's just 1. How many points you have more than 1? It's just 1. So we see in this case that alpha star of x is equal to beta of x. But if you see, if we make alpha the conjugate alpha, then we have that how many points, sorry, how many number we have bigger or equal than 1, that is 2. And then we stop. So this is 2, and then bigger or equal than 2, we have nothing. So this is 2, and this, so we see that alpha star of x is different from beta x. So this, okay, yes, this is a combinatorial description where we say that it's one of the combinatorial equivalents, that x is arithmetically Macaulay if and only if, it's just one of the if and only if alpha star of x is equal to beta x. So this is the last one. If you want to play with 2 points, I stop it here. So if you want to play 2 points, we have 2 points. And if you draw, we have 1 point. And then this is alpha of x, beta of x is stupid. This is 2 because I have 2 points and nothing. This is 1, 1 because it counts 1 and 1. And if you make alpha star of x is 1, 1. So this is beta. So, and one more thing, and the last, that the Hilbert function, the first difference of the Hilbert function has as many. When is a arithmetically Macaulay, you can draw how many points in the first, how many ones, as many points you have in each line. For example, we have 1 point here, and the first difference of the Hilbert function, we have 1. Here, we cannot do this. And the Hilbert function of this, the first difference, you can draw this, and this is just 1, 1. So this is the first difference. And you recover the Hilbert function. So once you have the arithmetic Macaulay scheme, they have this nice combinatorial description that you count your points, then put the ones, and this is, of course, there are theorems. They cannot be proved in 50 minutes. Sorry, I took 2 more minutes just to go to the end. Thank you.